Okay class, on from circles into polynomials. So what we have behind me is a progression of algebraic equations that we've seen from our middle school time up through high school. The very top of our list here, y equals mx plus b, is the standard y-intercept form of a line, right? And we knew that the m relates to our slope and the b relates to our y-intercept. Okay, then beyond that we have this ax squared plus bx plus c, and you should go, oh yeah, that's that quadratic one, and that's a quadratic equation. And from there we can learn a few things. This c now is our y-intercept, alright, and this a helps control the shape a little bit, whether the parabola is one that is opening upwards or one that is opening downwards, depends upon the positive and the negative values of a. And then I wrote this monster down here, which is the standard form of a polynomial function. Now I'll get to that in a minute. Let's go back up to the line. If you look back at the line, there are two things we don't know, an m and a b. Two things. And if you remember, in order to find the slope for a line, you need to have two coordinates, or 2 points. Alright, so let's just give 2 points generically here. So you had to have 2 coordinates to find the slope, and then you could use one of the points then to find the y-intercept. 2 points for the 2 unknowns. Well, it turns out that pattern can keep going, that I have 3 things I don't know in the quadratic. The a, which is the coefficient of x squared, the b, which is the linear component, or the coefficient of x, and the c, the constant. So in order to find an actual standard formula for the quadratic, you would need to have 3 coordinates. So you would have to have a third coordinate that comes in here. Maybe it would be the next letters of the alphabet, no big deal. Alright, well, you can imagine that if I wanted the next part of the pattern, instead of just having this dot, dot, dot here, I could throw in y equals ax to the 3rd power plus bx squared plus cx plus d. Well, there I have the 3rd power, a cubic, if you will, and it has 4 things we don't know, a, b, c, and d. So to find this cubic, we would need to have 4 distinct points. Now, careful with the word distinct there. Distinct means they have to be different points. So it's possible you have one that's listed twice. You can't use that one twice to find the formula. But we can see the pattern will continue. I could do the ax to the 4th, bx to the 3rd, cx squared, dx plus e. Well, if you're using the English alphabet, eventually you'll run out of letters. 26 letters in the alphabet, so I would have 26 different unknowns. Well, that would mean I have to have 1 less than that for the power, or the 25th power. Well, we want to be able to make mathematics expand an infinite amount of powers. We need to change how we're using our letters or our coefficients. So this formatting of using the letters in order for the alphabet needs to go. And it brings out this beautiful thing here. Alright, this represents the infinitely large polynomial function where the lead coefficient, the one that's in front of the largest power, alright, that's using subnotation now to say that this is the coefficient of that largest power. They're both denoted with an n. It's a sub n of x to the nth power. So if that were the 8th power, for instance, this would be a sub 8x to the 8th. If this were the 10th power, it would be a sub 10x to the 10th. If this was a to the 100th, it would be a sub 100x to the 100th. So this notation allows us to say which coefficient we are on based on the power that's on x. And then the next one down would be 1 less than n. If this were the 8th power, this would have to be the 7th power. 8 minus 1 is 7. A to the 8 minus 1 is 7. So you have a sub 8x to the 8th plus a sub 7x to the 7th. And you would keep losing a power until you get all the way down to your constant. This little plus dot 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 plus tells us there are all the middle terms are in there too, until we get down to the quadratic term, a sub 2x squared, the linear term, a sub 1x to the, hey, there's a little hidden 1 here, you don't see it down there, we don't have to write the 1, but that is to the 1st power, and then a sub 0, and really, this would keep the pattern going as well, it would be x to the 0 power. But x to the 0 power is 1, so we don't need to write that either, it's just the constant. So this monster is really beautiful in the way that it represents any standard polynomial function. Okay? A couple of things that go with this. The power, the lead one, this power that's the highest. The highest power is always what we call the degree. the highest power of n, of power of x, which is the nth, is the degree. Okay, and a couple more things that go with this. As you were seeing in the pattern, we always needed one more coordinate than the degree of the function. This linear function, which is degree 1, needed 2 coordinates. This quadratic, which is degree 2, needs 3 coordinates. This degree 3 cubic needs 4 coordinates. The 4th would need 5 coordinates. The 6th would need 7 coordinates. The 8th would need 9. Right? So we always need n plus 1 coordinates to define the polynomial of degree n. Okay, so that's one of its properties. And as we keep exploring here too, we find that these have certain shapes. For instance, the linear function. You know that looks like a line, a straight line. Okay? And on a straight line, you'll see that there are no minimum or maximum points. Okay, a point given close to the left or close to the right is always lower than or higher than the point I've chosen. So there's no minimum or maximum points. This parabola, which could open up or down, but for simplicity's sake, I'm going to make it open up, has one minimum point. One minimum point, degree 2, ooh, it's one fewer than the degree I have. This cubic function. Cubic functions could look like the very simple x to the 3rd function you remember, which has no mins and maxes, but it could also look like other results, some of them looking like this n, if you will, which is a cubic curve. And that one actually has one maximum point to the left and to the right is actually lower than that point, and one minimum point to the left and to the right is actually higher than that point. So those are local mins and maxes. That has 2 of those. Cubic could have up to 2. If I went to the next degree, x to the 4th, for instance, can look like this cool little w, all right, and that could be an x to the 4th degree polynomial, and that would have 1, 2, 3 mins and maxes. Now, an x to the 4th function could also look like just a very basic looking parabola, a little squattier on the bottom, but it could look like that, and it always has 1 min or max point. Well, it turns out that later on in pre-calculus, you're going to study exactly what pieces of the coefficients you need that will control how many mins and maxes you see. For now, I want you to know that the number of mins and maxes could be up to 1 fewer than the degree. So the min maxes are 1 fewer than the degree. That's a possibility. You'd have to check right now the graph to really see how many it does have. But then we would use a graphing calculator, plug it in, and give it a shot.